Okay, time to do some revision. First of all, of course, in your exam books, you've got a whole stack of practice exams, and when I get round to it, you'll have available, posted online, all of those other practice exams and so on. Just note that the VCAR 2019 Northern Hemisphere paper is not in your exam book, and we'll use that in class as a practice exam in class that you'll do during class time, and we'll mark and give you feedback on it. So try and steer clear of that one to get full benefit from that process. Typical exam grade allocations for the previous study designs, and then percentages have changed a little for this one. Note how you don't have to get huge marks to get quite reasonable grades. So chemistry is a good subject. You put the work in and you'll get results for. Now, as you're doing your practice exams, be a little bit systematic about it. You need to do some under time pressure. We've tried to get you used to being mindful of time, using your time efficiently over the course of all the SACs this year, but you'll need, of course, more practice at that. So do some under strict time conditions, but there'll be plenty of times when it's more useful to do them untimed, especially early on when it's more diagnostic. You're more using your practice exams to work out where your strengths and weaknesses are. Once you've obviously marked that you've completed it, and as well, once you've completed it, of course, it's much less useful if you just leave it at that. The real value you'll get out of it is by actually correcting it, seeing where you went wrong, and following up those things that you did wrong. That's really important. So go back to all your materials, come and see me, come and see Dr. Collette, come and see any chemistry teacher. Just get help if you need it. I think those last few are the really important ones that you need to be doing. Be a little bit organised with your time. You should at the moment be aware of where you are in the different topics, chapter by chapter, topic by topic. Use what you've done so far with practice exams and revision to just indicate to yourself which topics you're better on, which topics you're weaker on. Bottom point there, look after yourself. It's a crazy this year, and you've just got to be really determined to get through this year the best you can. Now, the exam, Monday the 23rd of November, 2.5 hours plus 15 minutes reading time. It's a long time, and make sure you eat breakfast first. If your blood sugar drops halfway through that exam, your brain will stop working as well, and you need your brain working in a chemistry exam. Bring water, clear bottle of course. Go to the toilet. Even though, if time's not a particular concern for you, if you need to go to the toilet during an exam, it's actually it's a good chance just to clear your head, get a breath of fresh air. I do toilet usher on some exams, and it strikes me when I do that just that couple of minutes spent walking up to the office to go to the toilet, walking back again, just must help sustain you through that 2.5 hour process. You're familiar with the structure of exams. There's multiple choice questions. In the case of the exam, there's 30 of them and 90 marks of short answer questions. That leaves you roughly 75 seconds per mark, as we've made the point through the year. and that means efficient use of time is really important. And as I've said throughout the year, start your writing time on section B. It's too easy to lose valuable minutes on multiple choice questions, that each question's only ever worth 1 mark, so don't fall into the trap of wasting your time there. You'll get the data book, of course, given to you. If you could bring them out after you sit your exam, that gives us a chance to give the students next year one of the most recent data books. There are the 5 areas of study, and normally each area of study is weighted equally. However, in this year, that's not the case. So this is actually printed in your revision books, but I forgot to update that bit and it's not true. The weighting this year, it's the weighting that there's ended up being for SACS as well. Unit 3, which was less changed, no topics were dropped out of Unit 3, nothing from the study design was dropped, so they increased their relative weighting. Unit 4 decreases relative weighting, and those last 2 outcomes decreased even more. So food chemistry had quite a bit taken out of it, so that goes down 15%. Experimental design was compromised by the fact that practical work was so difficult, that comes down 15%. So I'm sure many of you will appreciate the fact that experimental design will have slightly less weighting this year. Yeah, there are some benefits to this crazy year. So let's go on and do some questions. So, starting off with the first area of study, heat of combustion. So what have we done? We are doing methanol. So we've burnt 1.1 grams of methanol. Temperature's gone up by a certain amount with a certain mass of water. And we're going to calculate the molar enthalpy of combustion. So pause here, have a go at the question. Now, what do we see? We see how we're going to work out energy. Well, do we have a calibration factor or anything like that for this scenario? No, we don't. So that means we're going to have to use the specific heat capacity of water. So that is what we will do. Specific heat capacity of water, so we'll use Q equals mc delta T. That will give us Q. Then molar enthalpy of combustion means we want it per mole, so we'll have to calculate the moles of methanol and divide. So Q equals mc delta T from the specific heat capacity of water, moles of methanol, and then divide one by the other to get our value. Now, it's an enthalpy we're being asked for here. We're not being asked for the heat of combustion, we're being asked for the enthalpy. Therefore, we have to express it as a negative. And of course, units aren't specified in the question, so we have to make sure we include the units. But B, how does this value obtained compare with the accepted value? Suggest and briefly justify some improvements. Well, what's this accepted value they talk of? Data book, of course. What do we see in the data book? Negative 726, and funnily enough, a huge amount of heat's been lost. So you're going to come up with 2 effective ways of reducing heat loss. Okay, part C, give a valid hypothesis for this experiment. Well, I've got no idea. What could that be? Well, let's go back and look at all the context material we were given at the start of the question. An experiment was performed to compare the heat of combustion of different alcohols. So it's a difference between different alcohols. So straight away, that tells us what our independent variable was, the type of the alcohol, so methanol, ethanol, propanol, butanol. It was suggested that the number of carbons determined heat of combustion. Okay, so that's pretty much telling us what hypothesis we shall use. So we need to make a prediction about what effect the number of carbons will have on the heat of combustion. Well, fairly safe bet that increasing the number of carbons will increase the heat of combustion, and we need a reason for it, a justification for our hypothesis. And what have I come up with here? More energy stored in the bonds. As long as you've got any sort of a vaguely plausible justification, doesn't matter if the chemistry is not quite sound, it'll be okay, so long as it backs up what you say for your hypothesis. Okay, independent variable, what are we changing? Well, we're changing the type of alcohol, so it's pretty easy. Dependent variable, what are we measuring? We're measuring the change in temperature, heat of combustion, change in temperature. Then all the other things that need to be controlled. Mass of fuel burnt, volume of water, etc. Okay, question 2, multiple choice. What is the advantage of a biochemical fuel compared to the same compound derived from fossil fuels? So think about that one, pause the video, choose your answer. Okay, so biochemical fuel is the renewable fuels. What are they doing? Well, they're not adding the carbon dioxide in the atmosphere. That's the best thing about biochemical fuels. They're carbon neutral, so to speak. Now, which of these best indicates that? So first of all, A, let's look at A. No energy is used to extract and isolate a biochemical fuel from its source. Clearly wrong. What about B? The amount of energy per mole is greater for a biochemical fuel. Clearly wrong. They're exactly the same. Only the biochemical fuel is produced naturally in an endothermic reaction. Well, that's wrong. Photosynthesis produced the fuel originally, both cases. And they're all endothermic reactions, which is pointing pretty much at D. And D is the basic definition of a renewable fuel. So biochemical fuels are renewable, they're replenished quickly using natural processes. That is an advantage of biochemical fuels. Probably not the main advantage, but it is an advantage. So that's the best answer easily. All the other three are incorrect. Question 3. Boil water using pentanoic acid, which burns. We have an enthalpy. We need 74.9 kilojoules to boil our water. What is the minimum mass of pentanoic acid required? Okay, have a go at that question. Okay, well, first of all, we see that equation with the enthalpy. The first thing I seize on is there's a 2 there to produce that many kilojoules. So if we're going to convert that to a molar enthalpy before too much more, then we can work out, using our delta H formula, we can work out the number of moles needed. So that's the amount of energy we need, Q, that's delta H. Transpose the sulphur in, get that many moles, multiply by the molar mass, we get the mass, and clearly answer C. Bushwalker needs to boil some water using a small canister of butane, which burns according to the thermochemical equation given. This looks very similar to the previous question, doesn't it? In fact, same delta H. I wonder what happened here. Doesn't matter, it's a question we can do. If you didn't get the previous question right, let's hope you get this one right. Same trick, you've got to divide your delta H by 2. Oh, this time I should have picked that up myself. This time we've got a few in the data book. So we don't have to work with moles, we can work with grams. So we get the heat of combustion out of the data book, 49.7 kilojoules per gram. How many kilojoules do we want? Well, one divided by the other gets us 1.51 grams. So that's a case where a bit of quick thinking, which I sorely lacked, will save you a little bit of time. The direct conversion of chemical potential energy to electrical energy occurs in, what do you think? Pause the video, make your choice, and then see. Well, hopefully you remember that is the big stated advantage of a fuel cell. We're going from chemical potential energy to electrical energy. So we get energy out of chemical energy, we get electrical energy out of chemical energy in fuel cells and in thermal power generation, burning things. And a fuel cell's big advantage is it's got a much higher efficiency because of that direct conversion. Photovoltaic cells convert solar to electrical. Photosynthesis converts solar to chemical. What is the temperature of a 0.5 mole sample of sulfur dioxide gas that has a volume of 8 litres at 2.0 atmospheres? Okay, we've got a gas question here. So we're going to need our gas formulas. So go away and work out which one and do it. Pause the video. Okay, which formula are we going to use? Well, first of all, we see, do we have standard laboratory conditions? No. We're being asked for the temperature and we're given a different pressure. So that means PV equals nRT. We know N, we know R, we know V. P, we've got to convert into kilopascals. So we know that 100 kilopascals is 0.987 atmospheres. That's our conversion. Now we want kilopascals, we've got atmospheres, so in terms of that conversion factor, we're going to multiply our 2 atmospheres by the units that we want it in, divided by the units that we've got it in. So we want it in kilopascals 100, we've got it in atmospheres 0.987. That's how we get our 202.6 kilopascals. Once we've got that, straight into PV equals nRT, transpose, solve for T. Remember, the answer is going to be in Kelvin. You have to convert that to Celsius. Note they were both there in the question. Got to be careful. Question 7, when hexene is burnt in excess oxygen, carbon dioxide and water are produced in the mass ratio of approximately. I'll go away and work that one out, pause the video, and then I'll go through the answer. Well, this time the trick in the question is it's a mass ratio. It's not mole ratio, it's mass ratio. Now, how are we going to work that out? Well, we need to start off with mole ratio, and mole ratio, of course, is going to come from the equation. So we need a balanced equation. Pretty easy. Balanced equation for combustion. Number of carbons equals the number of carbon dioxides, number of hydrogens halved to get to the number of waters, and then go backwards to work out the number of oxygens. So what do we see? We see, in terms of the products, carbon dioxide and water, it's a 1-to-1 mole ratio. So equal numbers of moles of both of them, but not equal masses, because carbon dioxide is a lot heavier than water. So we're going to have a full solution. Yeah, it's good. Now the model mass, so it's 1-to-1 mole ratio, and 1 mole of carbon dioxide is 44 grams, 1 mole of water is 18 grams. So it's going to be in the ratio 44 to 18. Now none of those fit exactly, but if you divide that by that, you're going to get 2.4 something or other. Very close to 2.5, which is what you get when you divide 5 by 2. More gases. 120 mils ethane, 60 mils of oxygen, incomplete combustion, reaction shown. Temperature and pressure are constant. That's nice. The final gas volume will be. Have a go at that one. Pause the video, and then I'll go through the answer. Okay, so the trick to this is the fact that we've got constant temperature and pressure. That means the volumes will follow mole ratio. We don't have to worry about moles, we can just work straight in mils, so far as working out what's in excess, what's not. Now what do we see? We see 120 mils of ethene react with 60 mils of oxygen. So we've got twice as much ethene as oxygen. What does the equation tell us? Well, we actually need twice as much oxygen as ethene. Clearly we don't have enough oxygen. Oxygen is going to be limiting. That's why it's incomplete combustion. So, what do we see? We need half as many moles of ethene as oxygen. We've got 60 mils of oxygen. That means we're going to use up half as many mils of ethene. Divided by 2, we get 30 mils. 30 mils of ethene will react, 90 mils will be left over. If 60 mils of oxygen is reacting, that's going to produce exactly the same mils of water, 60 mils, water's a gas, steam, and 60 mils of carbon dioxide. So to work out the final volume, it's going to be 60 plus 60 plus the excess ethene of 90 gets us to 210, which is one of the answers there. C, I think. B. B, was it? Yep. Next question, which statement about petrodiesel and biodiesel is correct? Okay, well we know they're different chemicals. Petrodiesel is that assortment of basically alkanes with a few aromatic molecules. Biodiesel is methyl esters of fatty acids. So which is the best answer here? You think about that, pause the video, come back and I'll go through the answer. Okay, so first of all, statement A. Statement A on the face of it doesn't look too bad. Petrodiesel does indeed emit soot and emits more soot than other forms of diesel. However, it is wrong to say that biodiesel is pollutant free. Now, if there was nothing else that was remotely true, you might come back to that one, but no, that last part is definitely wrong. B, petrodiesel is produced by distilling crude oil. Yeah. Biodiesel is produced by esterification of fatty acids. Yep, that's a pretty good summary of how the two of them are produced. That looks good. C, petrodiesel consists of long-chain hydrocarbons. Yes. Biodiesel contains benzene and its derivatives. No. Petrodiesel also contains benzene and its derivatives, the aromatic hydrocarbons. D, petrodiesel has greater viscosity and hence flows more slowly along the fuel lines than biodiesel. Now we know there's a difference there between the two, but this one is just round the wrong way. It's biodiesel that has greater viscosity. These sorts of questions, I always go through each of the options. Sometimes it's not immediately, you don't pick up immediately on the critical part of the answer. So just go through them all before you commit yourself. Which of the following is true of a biofuel? Is a biofuel, sorry. Make your decision. Pause the video, make your decision, and then I'll go through it. Okay. Biofuel is something that's made from biological matter. And crude oil most definitely isn't biological matter. So that's wrong. Natural gas, again, is a non-renewable fuel. It's not a biofuel. Electricity from hydropower might be renewable, but it's not a biofuel. It's not made from biological matter. Clearly cellulose is. Ethanol produced that way would be a very good biofuel. The heat of combustion of a sample of crude oil is to be determined using a bomb calorimeter. All the students in the class are given the same method to follow. We used a bomb calorimeter. We put our crude oil in there with excess oxygen. That all looks good, nothing particularly critical there. From this experiment, the student could maximise uncertainty by having all students follow the same procedure, maximise validity by calculating heat of combustion per mole, accuracy by taking samples from different sources, precision by using a digital thermometer with a small uncertainty. Make your decision. Pause the video, make your decision, and then I'll go through them. Well, what do we say? A is most definitely wrong. That uncertainty will not be affected by that. It's the actual nature of the experimental procedure that will reduce uncertainty. Validity will be improved by having them all follow the same procedure. Validity by calculating the heat of combustion per mole. What fuel are we dealing with again? I think it's crude oil. We can't work out moles of mixture. Accuracy by taking samples from 3 different sources. Now that's clearly silly. 3 different sources of crude oil are going to have different composition. Precision by using a good digital thermometer is indeed the case. The random error in reading it will be eliminated. Well, it's an exam question. Only 49% got that. It's a bit of a worry. I think that's enough for today.